So let's take a look at integration by parts. Now a good indicator for when you should use integration by parts is when you're trying to integrate two functions being multiplied by each other and you can't necessarily use u substitution. So the formula for integration by parts is going to be the integral of u dv equals u times v minus the integral of v times du. So what you need to integrate will be on the left side of the equation, and what you can turn it into will be on the right side of the equation to evaluate. So notice we need four things here. We need the u, we need dv, we need du, and we also need v. So for this first problem, let's go ahead and evaluate the integral by using integration by parts with the indicated choices of u and dv. So u and dv is already given to us in this problem. So we have the integral of x times the natural log of x dx. U is going to be ln x, and then dv is just going to be x dx. So if I go ahead and rewrite the formula, once again we have the integral of u times dv. So this is the form that the integral is in currently, and so that's going to be equal to u times v minus the integral of v du. So let's go ahead and find, we've already found u and dv, now let's find du, or the derivative of the u equation, and v, the integral of dv. So du, or the derivative of natural log of x, is just going to be 1 over x, and whenever we derive u or we derive v, we always need dx at the end. So we have 1 over x dx, and then v is going to be the integral of x dx. Well, the integral of x is just going to be x squared over 2. So now we can go ahead and plug everything into the formula. So the integral of u dv, or the integral of x ln x dx, is going to be equal to u times v. So u is ln x, v is x squared over 2, so I'll rewrite it as 1/2 x squared times ln x, and then minus the integral of v, which is x squared over 2, times du, which is 1 over x. So if I go ahead and multiply x squared over 2 times 1 over x, we get x over 2, or 1/2 x dx. Now let's go ahead and evaluate this integral. So 1/2 can come outside as a constant, so we have minus 1/2 times the integral of x dx. Integral of x is just x squared over 2. X squared over 2 times 1/2, or negative 1/2, is negative x squared over 4. And so I can rewrite it as 1/2 x squared ln x, and then we have minus, I'll write it as 1 over 4 x squared. Since this is an indefinite integral, I need to add the plus c at the end, and that's the final answer. So now for number 2, we have the integral of the natural log of x dx. And so notice we aren't given a u and dv like in the previous problem, so we have to pick it ourselves. Now in this problem, I'm actually make u equal to the natural log of x, so then dv is going to be equal to dx. Now whenever you're using integration by parts, it's always helpful to pick a u that you can derive, because when you have u, you're trying to find du, and for dv, make sure you pick something that's easy to integrate, because you're also trying to find v as well. So if u equals ln x, du once again is going to be 1 over x dx. And then if dv equals dx, now the integral of dx is just going to be x. So v will just be x. So now we can go ahead and write out the formula. So once again, the integral of u dv, or in other words the integral of ln x dx, equals u times v. So we have x ln x minus the integral of v times du. So 1 over x times x is just going to be 1. So we're basically taking the integral of 1 dx, or just dx. Now the integral of dx is just x, so we have x ln x minus x, and then since this is an indefinite integral, we need the plus c at the end. So that's the final answer. Now it's actually a good idea to memorize the integral of the natural log of x, so you don't have to repeatedly use integration by parts all the time just to integrate ln of x. Now in the next set of problems, you might have to use integration by parts more than once, which gets repetitive and you can mess up very easily. So now comes the tabular method. And this method is much easier, especially when you're trying to integrate by parts more than once. So in the tabular method, you still have the same u, you have dv, and you have a plus minus. And so you're basically going to make 3 columns. Your u column, dv column, and plus minus column. So in the u column, you're going to derive. In the dv column, you're going to integrate. And for plus minus, you're going to alternate between plus minus. It first starts with plus. Now the good thing about tabular method is, unless you're forced to use the standard formula for integration by parts, once you learn this tabular method, you don't even have to worry about the other formula. So now there are 3 different scenarios for the tabular method, and I have 3 problems for this method, so each problem will show 1 scenario. So for number 1, we have x times cosine of 5x dx. So let's go ahead and actually use the tabular method. So once again, we have 3 columns. We have a u column, dv column, and then a plus minus column. Now for the u column, once again, we need to pick something that we can easily derive. So for u, I'm actually going to go ahead and pick x, because I can easily derive x. And for dv, I can easily integrate cosine 5x. So I'm going to pick dv as cosine of 5x dx. And then obviously we have start with the plus, and then we alternate for the sign chart. Now the first scenario for the tabular method is when you can derive the u column all the way until you get to 0. So right here, derivative of x is going to be 1, derivative of 1 is going to be 0. So now we go on to the dv column and we integrate each one. And so the integral of cosine 5x, now the integral of cosine x is sine of x. So the integral is going to be 1 over 5 times sine of 5x. And the integral of 1 over 5 sine of 5x, well, the integral of sine of x is negative cosine. So it's going to be negative 1 over 25 times cosine of 5x. And then for the sign chart, we can just alternate between plus and minus. And so now what we need to do, or how we evaluate this, is we start with the first term on the u column, so x. We go down to the right, and then go to the right, and circle backwards. And I'm going to do the same thing with the next row until I reach the bottom of the table. And then I stop right there. So now what we do is multiply the terms and include the sign at the end. So if we multiply x times 1 over 5 sine of 5x, we get 1 over 5 times x sine of 5x. We have a minus sign, so we say minus, and now we multiply these two terms together. So it's going to be a negative 1 over 25 cosine of 5x. We include that sign, so that's going to be plus, and then for the last row, we integrate the two terms that are together side by side. So we take the integral of 0 times negative 1 over 25, which is just going to be 0. Now the integral of 0 is just 0, so that cancels. And a minus a negative here will be plus. So the final answer, if I write on top here, is going to be 1 over 5 x times sine of 5x. We have plus 1 over 25 cosine of 5x. And then we have plus c, since it's an indefinite integral. That's the final answer. So now for number 2, we have the integral of e to the 2 theta times sine of 3 theta d theta. Now once again, we're going to use the tabular method. So we have a u column, dv column, and the plus minus column. And so for u, you can choose either one because it's easy to derive either one. Just go ahead and choose e to the 2 theta as the u. And then the dv is going to be sine of 3 theta, d theta. And then we start with the plus sign in the first row. Now realize that for the u column, we can't necessarily derive e to the 2 theta until we get to 0. So this brings about the second scenario for the tabular method. And that is we keep on integrating the dv column and we keep on deriving the u column until we get a multiple of the original integral. And so I'll explain that a little bit later, but first let's go ahead and derive the u column. So derivative of e to the 2 theta is going to be 2e to the 2 theta. Integral of sine 3 theta d theta is going to be 1 over 3, or negative 1 over 3, cosine of 3 theta. And we have a minus sign for the next row. Now let's keep on deriving here. So the derivative of 2e to the 2 theta is going to be 4e to the 2 theta. And then the integral of negative 1/3 cosine 3 theta is going to be negative 1 over 9 sine of 3 theta. And then we have a plus sign. And so we stop here now. And the reason why is if you look at the integral that we got started with, e to the 2 theta times sine of 3 theta, and now we look at the last column of u and dv, we also have the same e to the 2 theta sine of 3 theta. So I'm going to go ahead and write out the terms now. So once again, we start with the topmost u column, go down to the right and circle back. Same thing, and then we stop right there. Now I'm going to go ahead and multiply the terms together. So we get negative 1 over 3 e to the 2 theta cosine of 3 theta. The sign is a negative, so we can say minus, and then we go ahead and multiply these two terms together. So we get negative 2 over 9 times e to the 2 theta, this time sine of 3 theta. The next term is a positive, so we have plus, and the last row we multiply and put it inside an integral. So we take the integral of negative 4 over 9 e to the 2 theta sine of 3 theta. And then we have d theta because it's an integral. Now I'm going to go ahead and rewrite and simplify what we got after we evaluated the integral. So we get 1 over 3 e to the 2 theta cosine of 3 theta. We have minus a negative, so that's plus 2 over 9 e to the 2 theta sine of 3 theta. And then we do have a negative 4 over 9 as a constant, so I can bring that outside the integral and say minus 4 over 9 times the integral of e to the 2 theta sine of 3 theta times d theta. Now remember that when we integrated e to the 2 theta sine 3 theta using the tabular method, we got this entire thing. So now what I can do is set that equal to the original integral. So we have the integral of e to the 2 theta sine of 3 theta d theta. Now since both of these have the same terms inside of the integral, I can basically add this term over to the other side. So this is basically 1 times the integral, so we're going to add 4 over 9 times the integral. So 1 plus 4 over 9, or 9 over 9 plus 4 over 9, is going to be 13 over 9. So we get 13 over 9 times the integral of e to the 2 theta sine of 3 theta d theta equals this entire thing. And remember, we're trying to solve to find the integral of e to the 2 theta sine of 3 theta. So we need to get rid of this constant. So we can just go ahead and divide by 13 over 9, or multiply by the entire thing by 9 over 13. So now that we have the integral of e to the 2 theta sine of 3 theta d theta all by itself, the integral is going to equal, I'll go ahead and distribute the 9 over 13. So 9 over 3 is going to be 3, so we get negative 3 over 13 times e to the 2 theta cosine of 3 theta. And then here 9 over 9 cancels, so we have plus 2 over 13 times e to the 2 theta sine of 3 theta. Since this is an indefinite integral, I'll add the plus c, and that's the final answer. So now for number 3, we have the integral of ln x, the entire thing squared, times dx. So once again, we're going to use integration by parts, the tabular method. So u dv and then plus minus. Now for the u, I'll pick this entire thing to be the u, so ln squared of x, or ln x squared. And then for dv, I'll just have it be dx. And then the first row is obviously going to be a plus sign. So realize that we cannot derive the u column until we get to 0, nor can we find a multiple like the previous problem if we kept on continuing to derive u and integrate dv. So this brings about a third scenario and the last scenario of the tabular method, which is we stop at the first row we integrate and derive. So I'm just going to go ahead and derive u once. So the derivative of ln x squared, we're just going to use a chain rule, is going to be 2 ln x to the first times the derivative of the inside function ln x, which is 1 over x. So if I go ahead and rewrite that, we could rewrite it as 2 ln x over x. Now the integral of dx is just x, and then we have the minus sign. So we're going to stop right there. I'm going to once again go ahead and start from the top row of u, go down right to the right, and then circle back. And we only need to circle back once since we only had to derive and integrate for one column. And then we can go ahead and evaluate this. We're going to multiply the two terms, so we have x ln squared of x, and then minus, that's the next sign, and then we're going to take the integral of the last row multiplied together. So notice the x's will cancel, and so we have 2 ln x dx. Now I can go ahead and rewrite this as x ln squared of x minus, the 2 is a constant, I can take that outside the integral, minus 2 times the integral of ln x dx. Now here's where memorizing the integral of natural log is very beneficial. So I'm going to go ahead and rewrite the same term, so x ln squared of x minus 2 times the integral of ln x, which if we had memorized is going to be x ln x minus x. So the final answer is going to be x ln squared of x minus 2x ln x plus 2x, and then we obviously have to add the plus c. So for this next problem, we have to first make a substitution and then use integration by parts to evaluate the integral. So for number 1, we have the integral of the sine of the square root of x dx. So when talking about a substitution, we're basically talking about u substitution. So the first thing I'm going to do before I use integration by parts is we need to rewrite this integral, because we can't necessarily use integration by parts, it won't work at this moment. So I'm going to make u actually equal to the square root of x. And the reason why I do that is I'm going to solve for x, so then x equals u squared. And then what I'm going to do next is find dx, or the derivative of the x equation. So dx is going to equal 2 times u du, because once again derivative of u squared is 2u. And now I can substitute everything back into the integral. So we have the integral of sine of, now remember we made u equal to the square root of x. So we have sine of u times dx, which is equal to 2u du. So sine of u times 2u du. If I go ahead and simplify or rewrite it, we have the integral of 2u sine of u du. So now I can actually use integration by parts, or specifically the tabular method, to solve this. So once again, 3 columns here. We need the u column, dv column, and plus or minus. Now for the u column, I'm actually going to make my u equal to 2u, because we can go ahead and use the first scenario where we can derive u until we get to 0. And then for dv, that's just obviously going to be sine of u du, and then we have the plus in the first row. Now we can go ahead and derive 2u until we get to 0. So derivative of 2u is 2, derivative of 2 is 0. Integral of sine of u is going to be negative cosine u. Integral of negative cosine is negative sine of u. And then we have alternating, so plus minus plus. Once again, I'm going to go ahead and circle around these terms until we get to the bottom row. I'm going to stop there, and then we can evaluate. So I'm going to go ahead and multiply those two. So we get negative 2u cosine of u. We have a minus here. 2 times negative sine of u, so that's going to be negative 2 sine u. And then we have plus the integral of the last row. So plus the integral of 0 times negative sine u, that's just going to be 0. Once again, 2 negatives will make a positive. The integral of 0 is 0, that will cancel. And so then we get negative 2u cosine u, and then plus 2 sine of u, and then plus c, since this is an indefinite integral. Now, before I circle the final answer, once again, we have everything in terms of u. Now, for the original problem, we made the substitution that u equals the square root of x. So I'm going to go ahead and substitute that back in. So the actual final answer is going to be negative 2 times u, which once again is square root of x, times cosine of u, square root of x, plus 2 times sine of square root of x, and then plus c. So that's the final answer.